All right, this is Mr. McCord's ICP class, Unit 5, assignment number 2. We're going to be looking at the ionic compounds that we've been making by a give and take of electrons, getting things charged, and having them stick together in an attraction we call an ionic bond. But we want to look a little deeper into how we identify and distinguish ionic compounds from the elements that make them up. When we put elements together into an ionic compound, they're no longer the same as the elements that they were before. Sure, it's made of the same stuff, but their properties are totally different. Okay? Typically, an ionic compound is made of a metal, usually somewhere over here on the periodic table, and a nonmetal over on kind of the right side over here. Typically, your metals are the guys that like to lose electrons, they become positive, and nonmetals are the guys that tend to gain electrons and become negative. Then those positive and negative ions group up, they attract to each other. Okay? As a result, the stuff we get doesn't really act like a metal or a nonmetal specifically. It acts like some totally different substance with its own properties. So like the rust on this iron block here does not really act like the iron or the oxygen it's made of. You know, iron is shiny. This is dull and red and kind of scratchy. Oxygen is a gas that floats around the room and is invisible. Well, rust is certainly not invisible, and it's certainly not a gas either. It's a solid. Okay? So the properties of iron and oxygen together in an ionic compound are totally different. That metal and nonmetal combination form a different substance that is something new. So we want to call them a new name, and we want to give it a formula that shows what's in it. So we can identify that ionic compound as something new. Okay? Here's another example. This is the result of silicon and oxygen bonding together, where silicon's giving up its electrons to oxygen. This is quartz, or this is a kind of quartz. This is blue quartz. All right. Again, definitely doesn't look like oxygen. And this doesn't look like silicon, which we dealt with for a little bit in lab number 2. Was shiny and conductive, but very brittle, kind of a bluish gray color. It was a metalloid. Okay. Well, now, it's not conductive, but it is very sturdy. Quartz is very hard to scratch and even to break. Okay, one of the more stable materials you can find in the earth. Okay, and then finally, I have this salt substitute. Typically, the table salt that you eat is sodium. Well, I don't want to give that away. We'll find out what it's called in a second. But it's an ionic compound of sodium and chlorine. This is potassium and chlorine together. Okay, potassium is a very reactive metal. All right, chlorine is a very toxic green gas. If I pour some of this out of my hand, I'm not going to be inhaling toxic fumes, and I'm not going to be running away from a very reactive metal. It just looks like salt. Okay, so this new ionic compound doesn't have the same properties as the metal and nonmetal that it started with, potassium being the metal and chlorine being the nonmetal. Okay, so we want to show that these are different things by giving them a different name. All right, we're going to do here, and we're going to give it a different formula, which is how we symbolize the structure over here. How we take this information about how many ions of Na and Cl or Zn and S or Ag and N come together and kind of simplify it. Okay, first we're going to look at how we name ionic compounds. So here's what we do. We have elements that make up an ionic compound, like sodium and chlorine, or magnesium and chlorine, zinc and sulfur, and on and on and on. But just putting those two names next to each other isn't going to be enough. They still sound like the original elements. So I can't call this new ionic compound here sodium chlorine. Otherwise, that just sounds like I've got the two elements next to each other. But really, they've made a new substance. So to show that this ionic compound is something new that has its own properties, here's what I do. I leave the cation's name the same. So whatever your positive ion is, that element name stays the same. Anion. Okay. But then the anion, the negatively charged guy, is going to have the N chopped off and replaced with something else. The ending instead is going to be IDE. instead of the usual ending. Okay? So for something like sodium and chlorine together, sodium is my cation, it's my positive thing, so that stays the same. The first part of the name is still going to be the word sodium. Okay? But the second part, I'm going to chop the end off, usually after kind of the first like hard consonant, like the first like noise. So chlor, and that's where I'm going to cut it off. I'm chopping off this INE and replacing it with IDE. Okay, so this is going to be sodium chloride. Okay, chop off the end and replace it with IDE. Chlorine becomes chloride. Okay, so there it is all as one word, since I kind of chopped the end out there. Okay, with magnesium and chlorine together, magnesium is my cation now instead of sodium. So again, it's the positive thing. Magnesium is going to stay magnesium. That part will not change. The positive part stays the same. But chlorine is again my anion. It's my negative part. So I'm going to chop the end off just like I did before. And chlorine is going to become, again, chloride. Okay? So in other words, this is called magnesium chloride. Oops. Chloride. Okay? Not so bad so far. Okay. But what about when we have a Roman numeral like this? Like with the zinc and the Roman numeral 2. So the Roman numeral 2 is telling us that the zinc is giving up 2 valence electrons. It's going to have a positive 2 charge. So we're just going to leave it in the name like that. Okay? Roman numerals stay. After all, it is part of the cation, and the cation name is supposed to not change. So zinc Roman numeral 2 is just kept as zinc Roman numeral 2. And we just read this as zinc 2. Okay? So zinc 2. But then I have to cut the end off of my anion, my sulfur, and make it IDE. So again, kind of after that first like sulf part, sulf is where I'm going to cut it off. I want to put IDE there instead of this UR. So it's going to be sulfide. So the full name of this ionic compound is going to be zinc 2 sulfide. Okay? Still not too bad. Right? Let's do this one down here. All right? Silver, Roman numeral 1, same thing. We keep the Roman numeral, we keep the name the same for the positive guy. The only thing that's got to change here is our nitrogen. Now, this can be a little bit tricky. Like, do I chop this off at nitride or do I chop it off at nitrogide? Not super sure. Okay, again, typically it's that first kind of like hard consonant noise. The nitr is where we're going to cut it off, not at the nitroj. So kind of earlier the better. All right. So I'm going to chop this off at nitr and make the rest of it IDE. So this is going to be silver 1 nitride. All right. So some of these take getting used to. The more you write them out, the more you will remember them. You don't need to memorize them, but it makes it easier and easier the more you kind of practice them and use them and see them. Okay? So recognizing nitrogen becoming nitride instead of nitrogide is going to be kind of weird at first, but the more you do it, the more you kind of pick up on how it's supposed to sound. Okay? So there's a couple examples of how we figure out the names of ionic compounds. Let's take it a step further and figure out the formulas. Now, if you already have the structure of the ionic compound figured out, the formula is actually pretty easy because this was the hard part of figuring out what the stuff was made of. How many Ags and Ns is it going to take to make this happy ionic compound? To get all my charges to cancel and to get everything to either 0 valence electrons or 8 valence electrons. Okay? Now, the formula is just counting how many atoms of the positive thing and the negative thing I have. Okay? So, in a formula, we still put the positive cation first, but we're showing the symbols now. So let me put the letter don't see it already on there. Let's do X. Okay, so I'm just going to do an X to show my cation. It's positive. Okay, so I'm going to have an X, and I'm going to have a little number down here next to it, a little subscript, to tell me how many times that cation shows up in the structure, how many times it needs to be there to make everything else happy. Okay, the anion comes next, and I do the same thing. So I'm going to call the anion Y, just because. Okay, so same thing. I'm using the element symbol for it. So if this were nitrogen, I'd use a big N instead of a Y. Right? And then I put down there the number of times it shows up. Okay, so it's easiest to figure this out from looking at a structure. So let's look at our sodium and chlorine coming together to make sodium chloride. Right? Well, Na is coming first, because sodium is the positive ion in this case. So I'm showing Na. Right? Now, chlorine is my negative guy in there, so he comes second. And then I want to have a little number down by each to show how many times Na shows up and how many times Cl shows up. Okay, so Na shows up once. I have one Na ion here. So I'm going to put a little 1 down there. Okay, chlorine shows up once in this structure. So I'm putting a little 1 down by it too. And that's my formula. Now, it's kind of silly and redundant to show the 1, because we wouldn't put Na or Cl there if it didn't show up at least once. So a lot of times you'll see chemists kind of not show the 1 there, and they'll just write this as NaCl instead of writing out as Na1Cl1. Okay, it's just kind of the tradition of it. It makes it a little bit tidier. Okay, so that's what I'm going to do here. Instead of showing 1s, I'm going to erase them. They're kind of implied. I wouldn't show the Na or the Cl if it wasn't in there at least once. Okay, so that's my formula for my sodium chloride. We just write NaCl. Okay, well, let's do the next one and see how that goes. All right, magnesium chloride has magnesium as the cation, the positive thing. So I'm going to write Mg there. Magnesium only shows up once. Put a little 1 down there. I might erase it later. Okay, and my chlorine is in there twice. Okay, so I'm going to write Cl, but I'm also going to put a little 2 down here, because it shows up twice in the structure. I need 2 of them. Okay, so I'm going to show 2 of them in the formula. Okay, so the 1 is implied by writing Mg. You know, there's got to at least be 1. So I'm going to erase that. But I need to keep the 2 there, because I want everyone to know that there are 2 ions of chlorine in this structure to make this ionic compound. Okay? If I got rid of the 2, then people might see this as just 1 Mg and 1 Cl, and that's not a happy ionic compound. That doesn't get everything to have either 0 valence electrons or 8 valence electrons. So I can't do it that way. Okay? If it's a 1 as your little number down here, as your subscript, you can erase it. Okay? And that's how we're usually going to do it. Okay? But if it's any other number, like a 2 or a 3 or a 4, we've got to keep it there. Okay? Let's do another example with zinc and sulfur coming together to make zinc sulfide. Okay, well, if I were just looking at this name and I had to guess what it was going to turn out to be, this is what I would do. Oops. Since it says zinc 2, I'm going to put a little Zn and then a 2 down there. And then sulfur sulfide is an S. Done. But that's not right. Okay? And this is why we need to look at the structure instead of just looking at the name. Okay? That Roman numeral 2 tells us how many valence electrons something is going to give up, not how many times it's in the formula. We only have one zinc here, so I should not write a 2 in the formula. Okay? Okay? Otherwise, I'm being misleading about this. Okay? All I'm doing is counting how many ZNs and S's there are in this structure. Okay, so there's one ZN and there's one S. And I'm going to scooch these a little closer to each other. Okay, just like that. Okay, so be careful of that. I see that happen all the time. Okay, let's do one more. So down here I've got silver nitride, silver Roman numeral 1 nitride to be exact. So my positive thing is my silver. I'm going to write its symbol. Now, you have to be careful with some of these. Make sure you check it on the periodic table. Some of them have weird symbols. So silver is not something with an S. It's Ag, which is kind of weird. Okay, so Ag. And our anion is nitrogen, so we're going to put an N. And then I need to make sure to have the little subscripts, the little numbers down there to say how many times I have each of them. Well, I've got 3 silver ions. So I need a little 3 down here. Okay? Again, not a 1. I'm looking at the structure, and I need 3 ions. And that's what my formula tells me. I need 3 of those silver ions to come together to make this ionic compound work. Okay? And for our nitrogen, we only have 1. So again, I could write a 1. But it's implied. So I'm just going to erase it. Okay. And that's all there is to it. Okay? So if you've already got the structure, you're in the clear to figure out the formula. If you know what elements are in the ionic compound, you can make the name pretty darn easily. All right? Figuring out the structure tends to be the hardest part. Okay, but for now, these 2 are what we're focusing on. Okay? Okay, here's kind of a shortcut guide to figuring out what your anion should look like when you chop off the N and put IDE there instead. So a lot of them, like I said, kind of come after that first hard consonant noise, like a hard B or R or X in the case of oxygen. So like carbon becomes carbide, nitrogen becomes nitride, phosphorus becomes phosphide, oxygen becomes oxide, sulfur becomes sulfide. Selenium is really the one odd case that waits until the end, so selenide instead of selide or something like that. So selenium becomes selenide. We don't see that one very often. We don't use it very often. But the rest of them we do. Especially these last 4 are pretty common. Fluorine becomes fluoride. You've probably heard of that one at the dentist's office. Chlorine becomes chloride, like in sodium chloride, table salt. Bromine becomes bromide. And iodine becomes iodide.